Hello, it's Keith here, and this is lesson 9 of the basic series of my programming tutorials. In this series, we discuss basic concepts that you're going to need to know when you're looking to do programming. Now, I generally cover assembly language, but to be honest, this episode isn't really going to have any particular relevance to assembly in the sense that it would be perfectly appropriate for anyone looking to program any programming language. So we're going to be discussing graphics concepts today. We're going to be discussing the very abstract ones, just sort of very conceptual ones. We're also going to be discussing some specific stuff relating to hardware, how some kinds of old hardware work. So that's what we're going to be discussing today. Let's make a start and let's discuss the first concept. Now, the first concept I want to discuss is sprites. Now, what is a sprite? Well, simply in most common understanding of the term, a sprite is an object that moves around the screen. So the sprite might be our player, or it might be the enemy, it might be a mouse cursor, something like that. That's what's usually known as a sprite these days. Now, there are two kinds of sprite. There are hardware sprites. This is where the graphics hardware itself is drawing the sprite to the screen. And there is what's often known as software sprites. This is where our graphics hardware doesn't have any particular sprite drawing capabilities, and so we're having to manually plot that sprite to what is usually the bitmap screen. Now, some particular people will say there's no such thing as a software sprite, or only hardware sprites are sprites. Well, you can argue that if you want, but I don't think it's particularly helpful for learning how to program hardware and how hardware it can be used to make games. As I say, from the way I look at it, a sprite is a moving object that we want to move around the screen as part of some other game or program. So now when we need to think of sprites, and specifically hardware sprites, it starts to come into the next concept of tile maps. So let's move on to that concept first, and we'll come back to hardware sprites. Now, when it comes to talking about hardware sprites, we also need to start thinking about the tile map, because on a hardware sprite based system, usually there is another part to the drawing of the screen, and that is the tile map. So let's just go over to our theatre screen and have a look at this image here. So here we've got an imaginary representation of the two layers that you might see on a classic system, like, for example, the NES or the Game Boy, something like that. They would typically have one, or sometimes on the more advanced one, two or more tile map layers, which were a tile-based grid of graphics. These were usually 8 pixels by 8 pixels. And then on top of that, we would have the sprite layer, which were our moving objects. So here, I've represented these two as two visible physical layers, but of course, you would see them overlaid on top of each other in the actual game. So these two layers would be combined together to form our actual game image, which in our imaginary world is this game here, which is our sort of Super Mario game. So we've got our object here, our blocks that we might need to climb, we've got our stars in the sky, and we've got our player character. Now, in the case of this example screen, only the player character is a sprite. Now, on a hardware sprite system, it might not be a single hardware sprite. The hardware sprites would have very strict limitations to their size and their colors, and so it might be the case that we need to make this graphic, this single player character, out of multiple hardware sprites. Maybe we need 2 to double the height, or maybe our sprites are only 2 color and we need to overlay 2 or even 3 to make our color graphic as we want it. But from the point of view of the player, it would appear to be just a single object. Now, what is the difference between these hardware sprites and this tile map? Well, the tile map will cover the entire screen, and the way that the tile map works in sort of memory is that each one of the blocks of the screen will be represented by 1 or maybe 2 bytes, usually on these 8-bit systems. Now, in our original graphic, we had our grass, we had our climbable blocks, and we had our stars in the sky. Now, depending on how a game worked, the stars in the sky could be sprites, but on the hardware sprite-based systems, and this is the real limitation of hardware sprites, there tends to be a limit to how many hardware sprites can be on the screen, or even on a single line, and usually, honestly, both. Now, it's quite common to do things like, you need some stars on the screen, they're always there. You would use the tile map to do that. Now, the limitations of the tile map are that everything has to be in a uniform grid. So on a tile map system that uses 8 by 8 pixel tiles, which is the vastly most common one, each of these tiles would need to be equally aligned. So we couldn't have one of these stars 4 pixels across, because they have to be a multiple of 8. It has to be in an 8 by 8 grid, which is why our sprites are more flexible, but there is a limit to how many hardware sprites we can have on the screen, and there's no possibility that we can have sprites on every single square of the screen, except for a system like the Neo Geo, which has a huge number of hardware sprites actually has no tile map. You have to use hardware sprites to simulate a tile map, which is very odd, but that's really an exception to that system. Now, that's how we draw our screen on a hardware sprite-based system. So we would build up that screen out of the tile map backing and then the hardware sprites on top. Well, what about a system that only has software sprites? Well, those systems often won't have any tile map either, and so we would have to draw the entire screen out of pixel data, and we'll discuss the kind of formats you'll see for that in a moment. But the problem with this is it's slow. All of the data being transferred to the screen memory is being transferred by our processor. Now, with the hardware sprites, the drawing of the screen is being done by the hardware. So if we want to move our tile map by one tile or half a tile, what we can do will depend on the hardware, but the actual updating of the visual screen is entirely done by the hardware, so it's very, very quick. Equally, if we want to move our sprite across the screen, the parts of the screen that were under the sprite originally, they will be the tile map or other sprites, and the hardware will automatically recreate those parts that were covered before but have now been revealed. So there is no processing power needed to do that. On a software screen, on a system that we've not got no hardware tile map and no hardware sprites, redrawing that background area is going to have to be done by our software, and drawing the sprite into the new position is going to have to be done by our software. And that's why a system like, for example, the Amstrad CPC with its 4 MHz processor is vastly graphically slower than the Nintendo NES. It may have a reasonable processor, but it's got no hardware sprites that can do all of that work for it. So all of that work is being done in software. It's also why an Amstrad CPC game is often a lot slower than a ZX Spectrum game, even though the game has often been ported and the processor is the same. The ZX Spectrum screen takes half the amount of memory because it's got half the colors in a lot of senses. I know there's some technicalities there which we'll discuss in a moment, but as I say, that's where hardware sprites are very powerful and tile maps are very powerful, and that's the limitation of software sprites and software tile maps and things like that. There is, however, an advantage to software screens, bitmap screens, in another sense, and that's because they can do literally anything. As I say, the hardware systems that have a tile map and they have sprites, you're limited to this 8x8 grid system for the tile map, and you're limited to a number of sprites on the screen. On a bitmap-based system, there will be some kind of allocation of memory to the visible screen. Now, how this is allocated and the orientation will depend entirely on the hardware, and how much memory it takes will depend on the amount of colors that the current viewing mode has. So, for example, if we had a 256 color screen, then you would be usually using a single byte per pixel. If you were using a 16 color screen, you would be using 1 byte for 2 pixels, and if you're using a 4 color screen, you will be using 1 byte for 4 pixels, and if you're using a black and white screen or something like the ZX Spectrum, which allocate colors oddly, you're using on the Spectrum, you're using approximately 1 byte for 8 pixels, and so that is why these lower color systems, the systems with more limited colors, are often faster, because the amount of data that's used to make up the screen is lower, so updating the screen is faster, takes less time. Now, the advantage of these bitmap screens is they have no limitations, so we can do things like have a million sprites on the screen. It's just going to be a very low frame rate, whereas the Nintendo NES cannot do that. We can also do things that need more changes to the screen, more uniqueness to the screen than is possible on a system like the NES. For example, we can have a full screen rendered graphic, a vector wireframe graphic like the Star Wars game, things like that. The NES could do things like that to some extent. The Elite game did do that, but there was a lot of tricks involved in doing that, and usually when you are having 3D wireframe graphics on a system like the NES, you are actually having to use a smaller than the actual potentially visible screen area to do that. I do have an example of drawing line-based graphics on the NES. I did a little game called Photon, which was a light cycle type game, but as I say, you're usually quite heavily limited to the amount of screen area you can actually use, because as I say, you've got these problems with regards to the tile map will have its own limitations to the number of tiles that can be shown on the screen. So yes, as I say, bitmap screens are slower, but they are more flexible. Tile sprite based hardware systems are much faster, but they have other limitations, and that can sometimes force you to make design choices that you otherwise wouldn't have, and that's why you'll see on a system like the NES a lot of platform games, because Tile Sprite works very well on that, whereas on the Amstrad CPC you've got crazy games like Total Eclipse, Castle Master, and the space shooters like Elite and Star Wars that use vector graphics. A lot more flexibility for that reason. Now, as I say, bitmap screens will have some kind of allocation to memory, and those will be representing the pixels on the screen, but sometimes there is not entirely a one-to-one representation of the bytes of data and the resulting color graphics, and there will be some kind of color attributes. Now, what this is in most cases, it's kind of, if you're a bit old, maybe like me, you remember the teletext system, where there were characters and the characters had very bold, blocky colors, and this is something that you'll see on systems like the ZX Spectrum, and it's referred to as color attribute. Now, each byte will represent 8 pixels, but it will only represent whether those pixels are on or off. There will be one extra byte that will define a block of 8 times 8 pixels, so 8 bytes of black and white on and off data is then having a color attribute applied to it, and that is defining the final color. So you can see here in the case of this graphic here, which is from my Chibi Akumas on the ZX Spectrum, you will notice that there's very distinctive color changes here. The bottom half of this supposed heart icon is red, the top half is pink. And you will see here that the Chibico's face is white and the hair is purple. But you will notice that this bullet here has changed color to match the hair. And the reason for that is that the colors can only be applied on this screen system in 8x8 blocks. The color attributes on the ZX Spectrum work in an 8x8 block. So for example, here I've been quite cunning and I've designed my scroll graphic so that the lightning bolt is in 2 diagonal blocks, and so that can be green, and the scroll itself is in the other 2 diagonal blocks, and I can make that yellow. So I've had to design my graphics around these limitations to try and minimize the effect of them. You can see the eye here is in a different block to the skull's face here, and these worms here, these are green, whereas the brain of the skull, that is pink. So as I say, the color attributes are quite a clever way of giving more graphical capabilities than just the 1 bit per pixel bitmap data, but without massively adding to the amount of memory that the system requires. Now, the Spectrum's 256 by 192 screen takes 6 kilobytes of memory for the black and white data, but in addition to this, an extra just 768 bytes of color attributes are added to this to give the full color screen. Now, in comparison, the 4-color screen at 320 by 200 resolution, which is admittedly larger, of the CPC takes 16 kilobytes. So much larger, and even if we reduce that to 256 by 192, we would still take 12 kilobytes to do a 4-color screen, and that's twice the Spectrum's memory, and the Spectrum isn't a 4-color screen, it's capable of 8 colors and also brightness attributes. So by using these color attributes, we get a lot more flexibility for very little extra memory, even when compared to the black and white system, but it does give this what's often referred to as color clash of the systems like the ZX Spectrum. Now, not all systems work in 8x8 color attributes. The MSX1 uses 8x1, so each line has a separate color attribute, which allows for far more advanced colors, but of course uses far more memory. Now, a lot of systems, however much bitmap memory they have and how many colors they have on screen, will usually allow a larger range of colors to be selected from. So on our Amstrad CPC, for example, we might have a 4-color screen or a 16-color screen, but we're able to pick from a palette of 27. And a lot of systems, more advanced systems, or 16-bit systems especially, you will have a palette range of 32K or 64K colors, allowing a very large range indeed. It really varies depending on the system, but in most cases, you'll probably want to work on a retro system at 16 colors. That gives a good number of colors for your screen, but you will usually have a far larger palette to select from. Now, on systems like the Super Nintendo and some systems like the NES to some extent, we can actually use different palettes for different parts of our screen. For example, on the tile map on the Super Nintendo, we can assign a different 16 colors to each tile, and that can make the total screen have far more than 16 colors, which makes it look very good. And again, because we're only using 16 colors per tile, that keeps the amount of memory the tile definitions need quite low, which is going to help us out. But on the NES, the limitations are a little bit more odd. The palette definitions aren't defined for an 8x8 tile, they're actually defined for a pair of tiles horizontally and vertically. So 2x2 tiles, and that's why a lot of games on the NES, like Super Mario, for example, the blocks are all 16 pixel blocks. and that's because that's the definition level of the color attributes on the NES, typically speaking. So you will often see objects will be 16 pixels times 16 pixels, 2 tiles times 2 tiles, because that is the definition of the color attributes on that system, the palettes for the tile map itself. Now, in some cases, it is possible to bend the rules of the number of colors on the screen, and I actually did this with Chibi Akumas. Now, before we can discuss that, though, we need to discuss another concept which comes into play, especially with old hardware, and this is known as the raster beam. Now, if you're an old person like me and you have seen an old CRT television, you will know that they have a very slight flicker, and they do have a sort of a redraw. Now, basically, inside these, there is an electron gun which scans from top to bottom, left to right, down the screen very, very quickly at 50 or 60 hertz. And this is redrawing the screen, turning all the pixels on or off. There are phosphors at the front of the screen, and these will retain the image for a short period of time, but they need to be refreshed, otherwise the image will quickly fade. So that is how the beam runs. It starts, as I say, top left, scans across the screen, moves down one line, and it continues very, very quickly all the way down the screen. Now, why do we need to know about this? Well, this comes into play in a few places with regards to our programming. Now, as I say, on a system like the Amstrad CPC, we have a palette of 4 colors in 320 by 200 mode. But if we understand about this scanning of the screen and understand it's constantly going on, and we correctly time things very carefully, we can actually break the rules of what the hardware should be able to do. Now, here is a screenshot of the title screen of the Chibi Akumas game, episode 2. Now, you will see here, this is 4 color mode, but there are more than 4 colors on the screen. Well, how have I done this? Well, what the game actually did is it had very quick timed events during the redraw of the screen as that raster beam was scanning, and it changed the 4 colors that the screen was showing while the screen was repeatedly redrawing. So at the top of the screen, I set the background color to black, the color 4 to white, and I set colors 2 and 3 to pink and green. But when I got to this point, I changed them to purple and blue. There is actually one missing here. I then changed them here to be pink and blue so that I was able to draw the face here. I then changed them again here to purple and blue again. I then changed them here to magenta and pink, and then I changed them down here to pink and yellow. And this allows the screen to show all of these different colors on the screen, even though the screen should be just 4 colors. So the screen still is 4 colors because that is the physical hardware limitation, but I have bent that limitation by rapidly changing the colors throughout the screen, and this is what most hardware sprite systems do to some extent or another. A system like the Commodore 64 I think is only capable of 8 hardware sprites, but what the programmers would do is they would reposition those hardware sprites as the screen is redrawing so that they can appear in multiple places at the same time, and that allows the system to appear to have more than 8 hardware sprites. And in fact, most hardware sprite capable systems are doing this automatically in hardware. Usually you will see on a system like the NES, it's capable of 64 sprites on the screen, but you can't have all 64 on the same line. Well, why can't you have all 64 on the same line? Because the hardware is doing this kind of thing automatically. Because it's repositioning those hardware sprites as the raster beam is drawing the screen. It's doing it automatically and allowing automatically for 64 to be on the screen. So that is the raster beam, and that is how it affects the drawing of the screen and how we can trick it to take advantage and get more sprites on our screen than we should be physically able, and get more colors on our screen than we should be physically able. It can also be used to do clever tricks that you will often see on things like the Game Boy, which has this kind of redraw even though it's a TFT. You will see, I think it's Link's Awakening, you'll see the screen go all kind of wibbly. What they're doing is they are repositioning the tile map as the screen is redrawing, and that if you move the tile map as the screen's redrawing, you will effectively get parts of the screen looking wavy, and if you time it correctly and move it correctly, you will get a nice effect. So as I say, not just colors and sprites you can use this for. There's a lot of things you can use this trick of changing the screen during the redraw to get nice and interesting effects. Now, we've discussed there the raster beam drawing the screen, but it's also important to understand the blanking areas, and there's two reasons you want to do this. Firstly, you might want to do things like switch between screen buffers. We're going to discuss that in a moment, but there will often be times where you want to do things that you don't want to appear on the screen, and so you need to understand where these blanks are. But also with a lot of hardware based systems like the NES, you can't change certain things during the screen redraw, and you can only change them during what's known as V-blank. Now V-blank is vertical blank. As I say, the raster beam is going top to bottom, left to right, but when it gets to the very bottom of the screen, there is a small moment where it's not drawing anything, and then it will soon restart back at the top. That moment when it's not drawing anything is known as V-blank. Now there is actually a short period as well. When it gets to the top right hand side of the screen, it will need to jump back to the left, and at that point it's not drawing anything either, and that's known as H-blank. Now these, as I say, are useful for various purposes, but on a system like the NES, we need to wait for V-blank before we update our graphics, because if we don't, the tile map will actually reset its positioning and it will go crazy. On the Game Boy, we also need to wait for a blanking period to update the VRAM, but we can also use H-blank on that system. So as I say, there are cases where you'll need to know both. At this point though, it's worth remembering V-blank because you'll hear it an awful lot. It often is used for timing as well. There's usually on most of these classic systems some kind of interrupt at V-blank that we can hook into to control our sound, keep our music playing at a constant speed. If our game starts slowing down, our music won't. So even if it's not something you need to worry about for graphical purposes, you need to know the concept of V-blank because you will hear it. Now, some other concepts that we want to just quickly discuss, terms you will come across. The first one is CRTC. This is cathode ray tube controller. This is a hardware chip that some of these retro systems use, and it's used for configuring some things related to the screen display. Another term you might hear used is VDP. That is video display processor. You will often hear that terminology used on systems like the MSX. There's a lot of different terms that are used for the main graphics chip, but as I say, basically the important thing I think to understand at this point is the relation that graphics chip has to actually getting things onto the screen. So we've got our main CPU, which is our mathematical engine, if you will. This is doing our calculations for us. It's running our game code as well. Now, if our CPU wants to get a hardware sprite onto the screen, it can't do it directly. So what it needs to do is it needs to talk to some kind of video chip with a VDP. That will then talk to the VRAM, and it will read and write from the VRAM to update the VRAM and also get back from the VRAM what needs to be put on the screen when it's calculating the sprite. And that will be transferred to the hardware display system, the TV or the TFT on our Game Boy and things like that. So as I say, some systems call that the VDP. Others have another term, but it's basically our separate graphics chip unrelated to the CPU. Now, a system like the Amstrad CPC doesn't have one. It has only a bitmap screen, and we have to do everything in software, which is why it's a little bit slow. Okay, so we've discussed the hardware that is doing our drawing, but what about the actual way that data is stored in memory? Now, whether we're using a bitmap software-based screen or a hardware tile sprite-based screen, we're going to need to store data in memory that represents that graphics in some sense. Either our raw bitmap data of our screen or the pattern data for the tiles and sprites we may want to use. And there's basically two different ways that data might be stored on our system. Now, we're going to consider a 4-color screen here, but the way that we're discussing here would work in a very similar way on systems with 16 color or 256. So let's go over to our theatre screen and let's have a look here. Okay, so let's imagine we've got a screen and we're going to show 8 pixels on our 4-color screen. The leftmost pixel is color 0, which is white. The next pixel is color 1, which is green. The next pixel is color 2, which is brown. The next pixel is color 3, which is red. The next pixel is color 1, which is green, then green again, then color 2 brown, and then brown again. So we've got this sequence of 8 pixels. Now this is a 4-color screen, and so each of these pixels is going to need 2 bits to represent one of those 4 colors. And because we've got 8 pixels and 2 bits per pixel, we're going to need 2 bytes in total to represent these 8 pixels with their 4 colors. Now the question is, how do we want to store the bits that represent these colors in the 2 bytes? And we have basically 2 choices. Now, the most simple one might seem to be to store the 2 bits consecutively in a linear format. Now, for example, our color 0, both bits would of course be 0, so we could store those in bits 7 and 6 of the first byte. Our second pixel is color 1. And so we would store those 2 bits. The least significant bit is going to be a 1 and the most significant bit is going to be a 0. So that is 1 in binary. The next pixel is color 2, and that would be represented by 1 and 0. That's how 2 looks in binary. If you don't know your binary yet, that is the binary for the value 2, 1, 0. And our 3, both bits would be 1, so 1, 1. That's the binary for 3. And then our remaining 4 pixels here would be stored in the same format. So that is storing the bits in a linear format in our 2 bytes. So the first 2 bits here at the left of the first byte is the leftmost screen pixel, and the last 2 bits in the second byte here is our rightmost pixel. But there is another way, and this way is far more common with hardware-based systems like the NES. Now, instead of storing the 2 bits, the least and the most significant bit of our 2 bits that make up our 4-color system, we're going to split them up into 2 separate bytes. So we're going to store the least significant bit, the bit that's worth the least in the 2, and we're going to store all of those in a single byte, and this is going to be called bit plane 0. So the least significant bits are all being stored in this byte here. Now the second bit, the most significant bit, for example this one that's stored as a 1 here, this is going to be stored in the second bit plane 1 here. And so basically each of our 2 bytes now contains 1 bit for each of our colors. So our 8 pixels here are being represented by the combination of the 2 bits in our 2 bytes here. And so the rightmost pixel here, pixel 0, is being made up of the data in the bit 0 of both of these bytes here combined. Now, if we want to represent a color 0 in bit planes, both bit planes will be 0. If we want to represent the color 1, then bit plane 0, which is the bit 0 of the color 1, will be a 1, and the bit plane 1 will be a 0. And if you're wondering why that is, if you remember back here, we had the least significant bit was a 1 and the most significant bit was a 0, and here again the least significant bit is a 1, the most significant bit is a 0. Our color 2, well, bit plane 0 here will be a 0 and bit plane 1 will be a 1, because here the least significant bit was a 0 and the most significant bit was a 1. And the least significant bit here in bit plane 0 is a 0 and the most significant bit is a 1. Our color 3 will be a 1, 1, just like here it was a 1, 1. And you can see here pixel 3 is a 1, 0 and pixel 2 is a 1, 0. And just again here you can see the least significant bit was a 1 and the most significant was a 0. And you can see the opposite here for the opposite here. So as I say, in both cases we're using 2 bytes to represent our 8 pixels, and we are representing the exact same colors. It's just that the way we are storing the bits is different, and it's this concept of bit planes, or what I refer to as linear data. I couldn't actually find a specific term that was the correct one to use for this format where the bits are next to each other in memory, but as I say, I refer to it as linear data. Now the only thing is to mention is that there are some systems that use weird combinations. For example, the Amstrad CPC kind of uses bit planes. Basically the 2 nibbles of our screen are effectively the high and low bit plane, and the 16 color screen is a complete crazy layout. So I'm not trying to say that all screens that have 4 color screens store the bits in neighboring format like this, and you would expect a 16 color screen to use the top nibble, the bits here, for the first color and the bottom bits here for the second color. Some do, most do, not all do. As I say, bit planes are very common, and it was important to explain the difference between them because you will need to know about bit planes if you're working with most hardware-based retro systems. So there we go. Now the last concept we're going to discuss here is just the concept of screen buffers. Now screen buffers are simply the way that we work around the problem of if we're showing our graphics to the screen but we want to change the screen, and changing the screen is going to take a little bit of time, we don't want the user to see what's being drawn at the time. Now if you think of your classic 8-bit systems like the Amstrad CPC and your very slow games like Total Eclipse, which was a 3D rendered game, you were getting a 1 frame per second, yeah, literally, really, that was the frame rate. it's going to take a long time to draw that, and you don't want the viewer to see all of that being drawn. So what you do is you have two banks of memory. You are showing one to the user while you're drawing the other, and then you simply swap them over and you start redrawing the other one. So the user is always seeing the finished screen. The other screen buffer is being used to draw the screen up. And a similar concept exists with regards to tile maps as well. The Nest, for example, is capable of two tile maps, so you can be drawing a new tile map while the one is currently being shown. Depends what you need to do within your game, how you want to use things. Some games don't need screen buffers. If you've got a text adventure, well, you don't need that. A lot of the text adventures used to show the screen redrawing because they really didn't care. It wasn't important for them. And also screen buffers are an expensive luxury. They take a little bit of memory. So on a system with limited memory, it may not be possible to store a second screen buffer, and you might need to find other ways of doing it. One of which is especially clever, is to split the colors in two and to just simply make some of the colors the same as the background and update that part of the screen and then change the colors over. The Elite game on the Nest used to do that. That's how the Nest Elite game managed to simulate a screen buffer, simply by hiding what it was drawing by changing the color to black. So there may be times where you need to get creative to avoid using a screen buffer, but screen buffers are a common thing now. In the early days of getting started gaming, writing your own games on retro systems, screen buffers aren't going to be something you're going to need to worry about, but they're certainly something you should know about. So there we go. So that's the end of today's episode. I hope you've enjoyed it. If you're interested in retro programming, you can of course buy my book. It's called Learn Multi-Platform Assembly with Chibi Akamas. It covers Z86, 502, 68000, 8086 and ARM. But if that's not the CPU you're interested in, I do have a second book on the way covering another 5. So please check out my Amazon site and see if one of my books would interest you, because it's a really great way for you to help allow me to keep making this content. Anyway, I hope you've enjoyed it. Thanks for watching and goodbye.